Yeah.
And bonjour. This is the AI Biostat podcast with Bruno, Darko. But Darko is the guy behind the cat, although you could get confused by it because there's also the dark cat who is taking over. But you know, what are the rule of the world? You don't take cats what they do. And so we'll see how long Darko's cat is gonna keep us company here. Today we're going to talk about something that both Darko, myself, and the cat are super interested in, which is forest plots. And we want to describe how forest plots and biostats are used in the cancer field in particular, how LARVOL clean can be used to do Cochrane forest plot meta-analysis on the fly. And then, if we have time, we want to talk about a big project, which is how to power a forest plot with AI and to create the largest, humongous forest plot in the world, 40,000 hazard ratio in a single forest plot. We'll see if we have time today. So, Darko, welcome. Darko, what's the name of your cat?
Yeah, the name of the cat is Poppy, and
Poppy.
Poppy, yes, and she's
He
now
likes to pop in.
yes, she's the world's most famous cat right
For
now.
sure. For
Yes.
sure.
So, sorry. Yeah, so the
Ah,
Poppy will be joining us today, and as Bruno said, I may try to actually move the camera a little bit so
yeah,
that
it might be easier than moving the cat. Yeah,
yes,
for sure. Yeah.
the cat can never be moved because she's like the
No, it
boss.
cannot. Now,
She's the
now
boss.
here, Sheikh, a producer, might take offense to the fact that our heads are not aligned,
Yeah,
but
but
he'll understand. Force
yes,
majeure. The
Emergency,
cat did it.
emergency circumstances.
yeah,
I can
special
I can
situation.
increase. Right. So one word as you get ready to share, Clint. So you're the biostatistician. I'm the business guy who loves biostatistics, but I'm not a biostatistician. So I'm allowed to ask silly questions and to do things that are not accurate. But what I want to say is that we built at LARVOL a platform called CLIN, which is a Google map of cancer data, essentially. And one of the functions of CLINs is to be able to do is able to do forest plot on the fly. So think about it as a Cochrane, pairwise, meta-analysis on the fly, because we digitize all of the hazard ratios and all the metadata so that you can search by product, by trials, by endpoint, and create a forest plot on the fly. Now, of course, if you select the wrong trials, you're going to have a bad pairwise meta-analysis, and it's not going to be good. So uh, you can still do bad biostat by picking the wrong trial. So that's why I shouldn't do it myself. But we built the tool, and I'm going to have you demo it quickly, and then we're going to be able to talk about perhaps the largest forest plot in the world. So to you, Darko.
Yeah, so as you were saying, uh, we built this part of the data studio. So what everyone is seeing right now is actually a tab called Data Studio on Clin website, and among other things, one of the most important modules is the forest plot. We call it the forest plot because it's more convenient, but it's actually a meta-analysis module where users can quickly create a meta-analysis. So something that previously took me as a statistician maybe a few weeks to actually build can now be built maybe in a matter of minutes rather than weeks on Clean. And I will demonstrate that to everyone right now, and also maybe just bring up some important topics like hazard ratios, what they mean, and why do we actually use them very often in meta-analysis. So I'll be switching to Clean now, and under the forest plot tab, there are various ways we can try to create a meta-analysis, but the simplest way is really to think about the condition or type of the disease that we are interested in. So under the condition tab, I will type melanoma, for example. Just a moment, melanoma. And I should probably go deeper into melanoma as a condition because usually we're interested into a specific mutation or a subgroup, but for the sake of demonstration, I will just stick to general melanoma for now. And to create a forest plot is actually so easy that we can just, under these tabs here, we can see what subgroups for specific trials exist, and then we can choose some of them. Like if I choose this one, it will immediately create one hazard ratio for me in the forest plot automatically. And then I can do the same for some other trials. So basically in a number of clicks, I can create a small forest plot for now, small. And this is mostly me randomly clicking, but if someone is creating a meta-analysis, they actually need to decide, well, yes, this is the study that I'm interested in, and this is potentially the subgroup that I'm interested, like age less than 65, or maybe I don't want a subgroup, but I want a specific endpoint for the whole population. So we would need to align the endpoints. Again, right now I'm just randomly clicking to show the speed of creation of meta-analysis. Of course, all these endpoints would have to be aligned. So we can't use like I did right now. So I intentionally created a meta-analysis with different endpoints, but in real one, we would need to use, for example, only OS, only overall survival, or only progression-free survival, right? So, but again, I created a very quick forest plot in a matter of 2 minutes virtually. Now, if I had more time, of course, I would focus to align my endpoints. I would focus to choose the trials that are comparable to each other. So virtually in a matter of, I don't know, 20 to 30 minutes, I could create a quick meta-analysis here on Clin data tab. Now, why is this measure very important here that we have? It's actually a statistical metric. We call it the hazard ratio. So that hazard ratio is most of the time, especially in oncology, where we have survival data, which is so important, is used to evaluate the treatment effects of different drugs. So hazard ratio has a very specific way we interpret it. Usually the interpretation is such that if hazard ratio is less than 1, then we consider it as a beneficial treatment effect. So the lower the hazard ratio, the larger the treatment effect. And opposite also, if the hazard ratio is above 1, then we consider it as not being so good in terms of treatment effect. So you can see the first one here, it's above 1, right? So we wouldn't consider this as a very good treatment effect. And the last one, for example, from the keynote, where we have Keytruda versus placebo, it's a much better one. Another thing that we would need to align also in a meta-analysis is the comparators and interventions, right? So typically in a pairwise, this is the type of meta-analysis we call the pairwise meta-analysis. I would want, for example, on left side where we have the intervention, only to have one same intervention. Let's say it's Keytruda. So all of these would be Keytruda. And that's my research question, my hypothetical research question. I want to see if Keytruda is working better than some standard of care. So on the left side, I will have all Keytrudas, and on the right side, I would have all standards of cares. And then I would have a lot of these hazard ratios, and eventually I would get a diamond. What is a diamond? A diamond is the overall pooled treatment effect. So it is the treatment effect that we get by combining all these individual treatment effects from individual studies and essentially getting stronger evidence there, because we are combining so many studies. Now the evidence level is larger. And that is really the goal of pairwise meta-analysis. So going back to you, Bruno, what would you like to focus on here?
But first, I think we've been a terrific tool. I know I have a bias maybe, but I'm listening to you and looking at it. This is terrific. This is terrific. So, listeners, if you want to try a platform, please leave a message, uh, post a comment, or direct message us, and we'll demo. We'll give you a full demo, and maybe even a test access to the platform. So this is really terrific. As I was listening to you, I was thinking, is it fair to say there are two types of forest plots? One is the meta-analysis, where we want to take essentially a bunch of trials and try to summarize the overall effect. For example, it could be I don't know, IO versus a different kind of therapy in a certain tumor type, and we try to accumulate all the evidence we have into ultimately the diamond at the bottom that summarizes, does immuno-oncology works for a certain tumor type, right? And you do a meta-analysis to try to synthesize all the evidence we have for a certain research question. So that's a pairwise meta-analysis. Now, there is a second kind of forest plot that I want to mention. And in the forest plot, when you take a single trial, and for that single trial, you compare all the subgroups and see, and want to see essentially in which subpopulations does the drug works better, right? And so in CLIN, we also capture all the subgroups, or some of them at least. So there might be some interesting things to do with the subgroups as well. I'm brainstorming here. I'm not probably making a ton of science. I think it's a very exciting platform, and we'd love to demo it and share it with more people. Now, then I want to mention the second topic, which is exciting and which is going to be tough to completely describe in this podcast. So it's probably going to be sort of overflowing into the next podcast. And that's what we call the largest forest in the world. So our idea is the following. We have about 40,000 hazard ratio in CLIN. Nobody has that, by the way. I want to brag here with my fancy outfit. Nobody else has 40,000 curated hazard ratios in their database. Our job is to have every single hazard ratio, whether it's at the general population ITT level or at the subgroup level in CLIN. Right? So what we want to do is to build crazy forest plots where we have every single hazard ratio lined up. Now, visually in my mind, it's just exciting to see a 40,000 layer hazard ratio, but it's probably useless unless we apply AI to it, right? And so the idea that you and I discussed, Darko, is to say, okay, we have 40,000 hazard ratio. What can we do with machine learning? What we can do is train AI with a bunch of features, maybe some embedding, some vectorization, maybe XGBoost, one of the platforms we use for ML, for machine learning. We want to train our machine learnings to predict the hazard ratio. So in other words, we describe a trial, okay? We describe the population, we describe the intervention, we describe the control, we specify the endpoint, and voila. Our ML, based on its training on 40,000 rows of data, is going to, and some feature engineering, is going to deliver a prediction of hazard ratio, right? Now that prediction is backed by the fact that we tested our machine learning and shown that it predicts hazard ratio very well, maybe with a R square, a measure of quality of the prediction of, I don't know, 0.7 or 0.8, which is a great R square. So I'm the wild eye, bushy tail sort of business guy here, salivating on what we can do. You are the more grounded biostatistician and AI person. What do you think of the idea? Should we do it?
I think the idea is very compelling. You know, if you think about it, so many people have actually been thinking about a similar approach, but no one has had an idea how to do it. So just having even an initial idea right now live on the podcast, I think it's so interesting. And definitely, by the way, we have my cat is again trying to destroy my camera, so that's why I'm moving a little bit. Anyway, I think it's so interesting. With statistics is so it's so interesting because we always try to make things reproducible and validatable, right? But to create something like you said, a giant forest plot where we would essentially take 40,000 or 100,000 hazard ratios and then create a predictive model that can predict a hazard ratio that doesn't exist yet, right? So that's when you were speaking, that thought was going through my mind, which is, wow, this could be so interesting. We could use machine learning to predict hazard ratios that don't exist yet for the studies that have not yet been conducted, and the fact that we have so many hazard ratios, that we have this giant data set, actually makes me think that idea could be very valuable. Now, of course, it's not an easy task, but I'm always up to it.
Well,
I
the tough part was to curate 40,000 hazard ratios. Then he would lead you to drink. I mean, this is a monumental task. It took us many years to assemble that data set, and a lot of headaches, obviously. And now that we have it, I think we have to do it, Darko. We're gonna have to apply AI, train our machine learning on that data set, and see how well we can predict hazard ratios. Let's do it.
Let's do it. Let's
All
go
right.
for it.
All right.
Yeah,
Deal.
yeah, definitely. We got a deal.
If your cat let us do it though, because it's got a mind of its own, and it's judging us probably right now. It's probably judging my jacket. I can feel it. I
Yes,
can
she
feel it. Yeah.
actually all the time she was looking at you. So I was wondering why, and she's still doing it. Look, no, no, my cat. Wait, here is Poppy. She's looking at you right now,
Hey,
saying,
puppy. On,
Bruno.
yes. Look, it's change colors. Look, pretty cool.
She likes it.
Look.
She likes it.
All right.
Okay,
On,
back to
on
me.
that colorful note, Darko, we'll see you next week. We might continue to discuss a plan about how we're going to build the largest forest in the world and predict clinical trial outcomes with a great R square before running the clinical trial.
Yeah, I mean that would be so good. That would be
That's a big
huge.
deal. That's
I
a
mean,
big deal.
it's a big deal. It's a big mission, but hey,
Yeah,
we're Mission
we have to
Impossible,
do it. We're mission possible. That's right.
like Tom Cruise.
We fast on a mission. All right.
Fast on a mission.
Darko, thank you. And we'll see you next week.
Thank you and au
Au
revoir.
revoir.